Aime 2026. This problem involves a rotation that, intuitively, can lead to a lot of trigonometry, like compound angle formulae.
Using a rotation matrix could also work, but complicated. Today, we will use a simpler approach.
We have a 13, 14, 15 triangle. We rotate it until side A'C' is vertical. Then we need the area of the resulting hexagon AA', CC', BB'.
The trigonometry and rotation matrix approach involves complex calculations and is time-consuming.
I will use coordinate geometry to find the coordinates of A', B', C' directly. To rotate the triangle, we first need to find the center of rotation. Let's place our 13, 14, 15 triangle on the coordinate plane. We need to find the circumcenter. This point is equidistant from all three vertices. The base is on the x-axis from -5 to 9, so its midpoint is at x equals 2. The circumcenter must lie on this vertical line of symmetry.
Now we calculate the y-coordinate of the circumcenter D. We equate the squared distances from D to A and from D to C.
We use the distance formula. Solving for y, we find that the y-coordinate is 4.125. Substituting this back gives us the squared radius. The squared radius is approximately 66.02. We will use this value in the next step. We rotate the circle until the chord A'C' is vertical. Its length is 15. We must find its distance from the center. Using the Pythagorean theorem with the radius 8.125 and half chord 7.5, we find the distance. The distance from the center is 3.125. To find the coordinates, we move horizontally from D by this distance. Then we move vertically by the half chord length. This gives us the coordinates of A' and C' directly. Using rotation matrices would be very time-consuming. The coordinate geometry approach is much faster. The area of the triangle is invariant under rotation. It remains 84. The base AC' is a vertical line of length 15. Using the area formula, we calculate the height to be 11.2. Since the base is vertical, the altitude must be horizontal. Point B is located 11.2 units to the left. We subtract 11.2 from the x-coordinate to get -6.075. Now we find the vertical position. We use the right triangle with hypotenuse 13 and horizontal leg 11.2. The Pythagorean theorem gives us a vertical leg of 6.6. Subtracting 6.6 from the y-coordinate of A' gives 5.025. Thus, B' is at -6.075, 5.025. With the coordinates, calculating the area of this hexagon is easy. We can use the Shoelace formula to calculate the area. We sum the diagonal products downwards, then subtract the sum of diagonal products upwards. The difference between the sums is 311.4. Dividing by 2 gives 155.7. Geometry often relies on finding key invariants like area. What do you think about this method? Let me know in the comments below. Also, if you have any questions you want me to solve, leave them in the comments too.